Hi everyone, in this video I'm going to go through finding Marshallian, which is sometimes called uncompensated demand when we have a Cobb Douglas utility function. And I'm going to show you that with this utility function here, we get these demand functions here. So I am demonstrating a very abstract account of finding demand. So our abstract form of Cobb Douglas is utility is equal to some big A times x1 to the power of b times x2 to the power of c, where here x1 and x2 are good 1 and good 2, and big A, b, and c are all parameters. I'll also use an abstract budget constraint, so m, that's income, is equal to the price of good 1, P1, times good 1, X1, plus the price of good 2, P2, times good X2. Another way to express Cobb Douglas utility in the abstract is to normalize the exponents so that they add up to 1. So something like this. So A times X1 to the power of B times X2 to the power of 1 minus B. And so here clearly B plus 1 minus b is just equal to 1, so they add up to 1. So what I'll do is that I'll discuss this case right at the end of the video. When we look to find Marshallian demand for a good, what we want is an expression that tells us about the optimal level of consumption of the good, so that's our xi star, as a function of prices and income. So that's the goal, and you can see that that is achieved here in these functions. We find our optimal value of x1 and x2 as a function of the prices of the goods and income. The steps to finding Marshallian demand is to firstly impose our optimality conditions, which in the case of Cobb Douglas is just to set the marginal rate of substitution equal to the ratio of prices. We can then substitute the result of that condition into our budget constraint, and then we can solve for x1 star and x2 star. That's our optimal levels of consumption. All right, so let's start with step 1. So Cobb Douglas is always going to have an interior solution where the optimal bundle will be where the slope of our indifference curve, which is the negative of our marginal rate of substitution, is equal to the slope of our budget constraint, which is the negative of the price ratio. So the negatives cancel out here, so this reduces to the condition that I described before. The MRS itself is found by taking the ratio of our marginal utility of good 1 divided by the marginal utility of good 2. So let's find these marginal utilities first. The marginal utility of good 1 is equal to the partial derivative of our utility function with respect to good 1, and that will be equal to, we take b, that exponent on x1, and that can come out to the front. We leave a as is, and then that's multiplied by x1 to the power of, we take 1 off the exponent, so b minus 1, and that's multiplied by x2 to the power of c. The marginal utility of good 2 will be equal to the partial derivative of the utility function with respect to good 2, so that's equal to, well, c, the exponent on x2, comes down to the front. We leave a as is, that's multiplied by x1 to the power of b times x2 to the power of c. We take away 1 from the exponent, so c minus 1. So our MRS is equal to, well, I'm going to substitute in the marginal utility of good 1 and the marginal utility of good 2 into the ratio. So marginal utility of good 1 is equal to b times a times x1 to the power of b minus 1 times x2 to the power of c. And we divide that by the marginal utility of good 2, which we found was c times a times x1 to the power of b times x2 to the power of c minus 1. So those big A's are going to cancel out. I'm going to simplify this expression now a bit more, but I'm going to need to use some rules of exponents to clean up all of the rest. The first rule that I'm going to use is this one here. If I have, say, 1 over some a to the power of b, that's equal to a to the power of negative b. So if we have some terms with exponents on the denominator, we can move it up to a numerator spot if we introduce a negative onto those exponents. So with our equation, I'll leave the ratio b over c out the front, and I'm going to write out the terms on the numerator just next to that fraction. So x1 to the power of b minus 1 times x2 to the power of c, And then I'm going to move the variables that are in the denominator. We can put them up next to those other terms if we introduce a negative to their exponents. So the x1 to the power of b will turn into, well, x1 to the power of negative b. The x2 to the power of c minus 1 will turn into x2 to the power of negative c minus 1. And this exponent itself, if we just distribute through that negative, will reduce to negative c plus 1 or 1 minus c. The second rule that I'm going to use is this one here. If we have a to the power of b times a to the power of c, so we have the same base multiplied together, we just add the exponent. So this is equal to a to the power of b plus c. So with what we've got here, for instance, we have the x1 base twice, so they are multiplied together. So we have x1 to the power of b minus 1 times x1 to the power of negative b. So that's equal to x1 to the power of b minus 1 plus negative b. We also have x2 twice, so we have x2 to the power of c times x2 to the power of 1 minus c. So we add those exponents and we get x2 to the power of c plus 1 minus c. So the b over c ratio is still hanging out at the front. In terms of the run of variables that we're left with, the b's on the exponent on x1 cancel out, so we get x1 to the power of, well, we're left with negative 1. And the c's on the exponent on x2 also cancel out, so we end up with x2 to the power of 1. Now this x1 to the power of negative 1 can be brought down onto a denominator, and that allows us to remove the negative. And we also at this point don't need to notate when we raise any base to the power of 1. It's redundant. So we end up with our marginal rate of substitution being equal to b over c times x2 over x1. And this result is kind of a general result. For Cobb Douglas, if we want the MRS, we can take the exponent on x1, which is b in this case, we divide it by the exponent on x2, which is c, and that's multiplied by x2 over x1. Right, the next thing we're going to do then is just set this, our MRS, equal to the ratio of prices as per our optimality condition. So from this condition, we are then going to solve for either x1 or x2, and then we substitute that expression back into our budget constraint in step 2. I'm going to solve for x2, and we end up getting x2 is equal to p1 over p2. I multiply out x1 and also c, because they're on the denominators, and I divide by b, and that gets me x2 is equal to p1 over p2 times c times x1 divided by b. So that's really step 1. In step 2, we're going to use that condition we just found. We're going to substitute that into the budget constraint. So here's our condition we found before. And well, we get from our budget constraint, M, our income, is equal to P1 times X1 plus P2 times, well, X2 is equal to, we just found out, P1 over P2 times X1 times C over B. Now, immediately, the price of good 2 cancels out, so P2 on the numerator and the denominator there, that cancels out. We can then multiply both our left and right hand sides of our equation by B. So we get B times M is equal to, well, that first term, P1x1, will be multiplied by B. And then we add to that, well, P1x1 times C, that had B on the denominator, but if we multiply that by B, that will cancel out. So we just leave that last term as is. Let's factor out now P1 and X1 on the right-hand side. They're common terms. So we get B times M is equal to, we factor out P1 X1 times, we are left with B plus C in our parentheses. We can then divide out B plus C, and we can also divide by P1, so we get X1 is equal to, I'll put B over B plus C together times M over P1. So this here is X1 star, our optimal quantity. That's the quantity of X1 that our consumer should buy. And this is our Marshallian demand for that good for X1. We have this optimal quantity as a function of prices and our income M. And although actually you can see here with Cobb Douglas actually that the optimal value does not depend on the price of good 2. So P2 doesn't make an appearance in the demand for good 1 when we have Cobb Douglas. So sometimes you might see this notated as X1 star open brackets P1M because there is no P2 in the demand function. But it really depends what text you're using if they notate it like that at all. And really what we've done is kind of half of step 3 as well, because we solved for the optimal value of X1. We do need to solve for the optimal value of X2 as well to get the demand for X2. And we can solve for good 2 by either substituting this expression for X1 back into either our budget constraint or alternatively up into this condition that we found in step 1 again. So I'm going to put it into the condition we found into step 1. So if we do that, well, that will give us X2 star is equal to P1 over P2 multiplied by, I'll put C over B next, and that's times by X1 star, which we found was B over B plus C times M over P1. So you can see from this equation that the P1s and the B's will cancel out and we are left with C over B plus C, I'll put that together at the front, times M over P2. So that's our demand for good 2, and it's incredibly similar to our demand for X1, except C is on the numerator instead of B, and P2 is on the denominator, not P1. And that's how we get to our Marshallian demand functions when we have Cobb Douglas. Now, how does this change when we use the abstract version of Cobb Douglas where the exponents add up to 1? So if U is equal to A times X1 to the power of B times X2 to the power of 1 minus B. Well, here is our demand function that we found before for X1. But what I'm going to do here is that in our revised version of Cobb Douglas, C is now 1 minus B. So I'm going to replace that out. So this reduces to B divided by B plus 1 minus B times M over P1. So the B's cancel out and we get X1 star is equal to B times M over P1. So it's a simpler expression. It's kind of neater. For X2, we can do a similar thing. We found that the demand was equal to this here, but C now is equal to 1 minus B. So let me swap it out. So we have 1 minus B on the numerator there where C was. And again on the denominator, we get B plus 1 minus B. So those B's cancel out again and the denominator reduces to 1. And the demand for good 2 is equal to 1 minus B times M over P2. And so when we get this special case where our exponents on our Cobb Douglas utility function add up to 1, then our Marshallian demand functions, they actually come out quite elegant, quite reduced. So that's it. Please like and subscribe. Thank you so much for watching my stuff. You can also visit my website now, www.econhelp.com.au, for more resources to help your study. Thanks a lot, guys. Have a good one.